Yeah. Okay. So this is vectors number 19. And it looks something like this. You have a beam that makes an angle of 45 degrees with the horizontal. And then down here, that pin makes an angle of 20 degrees with the vertical. Well, the pin doesn't. So that pin can slide in a slot. Okay. And this angle is 20 degrees. And this angle is 45 degrees. And the length is 4 meters. Okay, so the first thing it asks for is we want to come up with a force vector that has a magnitude of r and is perpendicular to that slot. Okay, so how are we going to come up with, so for A, and then for B, we just want a vector that goes, I think, from the wall pin to the slot pin. Why would we want to, first of all, why would we want a force vector that's perpendicular to the slot with some magnitude that's a variable? We don't know what the magnitude of that force is, but if you think of what that pin in that slot does, it restricts the motion of this point in the following way. It allows it to rotate freely, right? Because it's a pin. This thing can spin. You could spin this like a top if it wasn't connected here, right? So this pin and slot doesn't affect rotation. So there's not going to be any moment provided to restrict rotation. It doesn't prevent any translation along the slide. It can just slide freely like that, right? But one thing it does is it restricts motion perpendicular to that slide. Okay, so we know that the force applied to this object is going to be perpendicular to that slide. We just don't know what the magnitude is. Okay, so that's why it would be relevant. And so how are we going to come up with that vector? Here's how I like to do these. I think this is a nice systematic way to do this. So here's our coordinate system. Just start with something that you're given, an angle that you're given, and then just hop around from reference to reference as it's given to you. So we know that what we're trying to do is come up with a counterclockwise angle from the x-axis to the vector we want, okay? Because then we can just use cosine and sine. So first I'm going to draw a vector with its tail at the origin that's along this slot. And it doesn't, there are two vectors that are along that slot. I could do one that's up and to the left, or I could do one that's down and to the bottom, and it doesn't matter which one I do, but I'm gonna do this one because that's the angle that's given explicitly, is that this angle is 20 degrees. Okay. And now we know that we want a vector that's perpendicular to this one. That's the vector that we really want. So now I'm going to draw a vector perpendicular. You know, these two are 90 degrees apart. And we want the counterclockwise angle from the x-axis to this vector. So now what's that going to be? You can think of it this way. Start in the direction of the positive x-axis. Go clockwise 90 degrees. So that's minus 90. Now go counterclockwise 20 degrees. So we're at minus 90, minus 70. Now go counterclockwise another 90. We're at minus 70. That puts us at positive 20. And so the angle that we want is positive 20 degrees. So I'm going to think of this angle. Theta is equal to negative 90 plus 20 plus 90. And so you just get an angle of 20 degrees. And so a unit vector in that direction is going to be cosine of 20, sine of 20. So that's 0.940, 0.342. And so that force vector then, since this is a unit vector, we can just multiply now by the variable r, and we know that the magnitude is going to be r, and the direction is going to be the direction we want. So this comes out to 0.940 r, 0.342 r. There's another answer that's perfectly acceptable, because notice we're talking about, we want a vector that's perpendicular to this, right? Well, I drew one that's perpendicular to it, but there's another one that's perpendicular to it, the exact opposite direction. So a perfectly good answer would also be negative 0.940 r, negative 0.342 r. Okay? Anybody have any questions about that? Yes.
Is the vector from the wall pin to the slot pin just like the length of the rod connecting them?
It's the length times the cosine and sine of the angle. You can also think of it as, there are two ways you can think of it. You can, if you know that angle, we know this is 45 degrees. We want the vector going like this from the wall pin to here, okay? So for part B, you could think of it like this. Here's our coordinate system. We're given that the vector we want makes an angle of 45 degrees with that negative y-axis. That's what's given on the diagram. And so to use cosine and sine with this, the theta that you would want would be, you could think of it as 180 plus 45, so 225 degrees. The unit vector in that direction, I'll call it u hat, the hat means unit vector, is going to be, cosine and sine at 225 degrees, that's going to be negative 0.7071, negative 0.7071. I don't know why I do those to so many significant figures, but it's superstition. I just have done that for a lot of years, and I'm going to keep doing it, I guess. And then, so the final vector that we want is 4 times that unit vector, which is, do I know what that is? No. Can someone multiply, what's 4 times 0.7071?
It's 2.8, isn't it?
Yeah, somewhere around 2.8 for sure. Negative 2.8, 2.828, right? 2 point, I don't know. But you guys are all good at multiplying. Okay. Any questions about either of those? Yes?
If we use instead of 225, 25 doesn't matter.
Well,
Like
I'm sure you've done so much trigonometry. Everybody has ways that they're used to doing it. So if you have a way you're comfortable with, feel free. This is a way that always works, so I like it. This can be a helpful approach, I think, in cases where you want a vector that's a reference to some vector that's a reference to some vector, because you can just hop from thing to thing to thing, and then you get a final answer at the end. You know what I mean? Like in this part A, like the way we did that is like, okay, well, we're not given the angle between the vector we want and a coordinate axis. We're given the angle between the vector we want and something else, and that thing is given relative to an axis. So this way of thinking about it, let us hop from, okay, first we hop from here to here, then we hop from here to here. You just keep adding those numbers, and it gives you something at the end you can use. Yes?
Is there a significance to the value for the variable, I should say, like t versus r?
Well, I use t's for, if you think of, they're just variable names. But people tend to use t's for things that are pulling, and r's for things that are pushing. That's sort of, you'll see it organized that way a lot. But really, just remember they're just variables. You could call it x or z or whatever you want. It's a variable. You know, mostly the names of the variables are just a way to communicate with someone else who's looking at your work. You know, they see R and they're like in their happy place. You know, they've seen that a million times. Any other questions about that one? Any other homework questions you'd like to see? Okay. So now we're going to, we've talked about vectors, talked about differential equations and stuff. So now we're going to get into the first topic of dynamics. So the first dynamics topic is kinematics of a particle in a non-rotating coordinate system. There's a lot in that name, so let's just make sure we understand what all that stuff means. Kinematics, what does kinematics mean? Yeah, that's describing the motion without worrying about the causes. So you can think of that mostly as positions, velocities, and accelerations. So position, velocity, acceleration, without forces, moments, or energy. This is all stuff that you could, if you had a carefully set up room with rulers everywhere and you had a video of things, you could do all the kinematics based on what you measure from that video. You don't have to know any masses or forces. Oh, I didn't say mass. We're not worrying about masses either. Okay, and what's a particle? So a particle is just a mathematical treatment of a body. With no length dimensions. Or orientation. So, if you have no length dimensions, you can't tell what part of an object is its head and what part is its feet, and, it's just a point. So you can't tell which way it's facing. It does have mass, though. We're going to always assume that, so if the location of a particle is just a point in space, that point is always going to be at the object's center of mass. So the point is located at the object's center of mass. We'll see later on why the center of mass is so important. There's just a lot of important stuff about the body's center of mass that we're going to use all the time. This is something important that maybe you haven't thought about before. With Newton's laws, you can treat anything as a particle. So, in other words, it doesn't have to be small or anything. If you don't care about its orientation. So an example of that is like when people do planetary dynamics, they tend to treat planets as particles. And they just don't worry about the fact that the planets are spinning. They don't care about that. So if you're not worried about what direction Jupiter's spot is going to face, you're only worried about gravitational interactions, then these things are bigger than the Earth, but you can treat them as particles. Okay. Be careful, though, if you're using energy approaches. Treating big things as particles can mess you up with an energy approach. Well, we're not focusing on energy approaches in this class anyways, so that's not going to bother us. Okay, but the reason you have to be careful when you're using an energy approach is like it all lumps up into the same thing. With Newton's laws, you do the translational equations of motion, Newton's second law, separately from the rotational equations of motion. So you can just, they're totally independent things. But the kinetic energy of a body is the translational kinetic energy of its center of mass plus the rotational kinetic energy, and you can't separate those two. Okay. All right, and there are 4 things that we're going to do in this, sort of 4 subsections to this topic. The first one is that the acceleration is the time derivative of the velocity, is the second time derivative of the position. So I'll say a few things about that. Oh, before I continue with these 4 sections. The last thing that I didn't say about this title is the non-rotating coordinate systems. You know, we've talked about that a little already. I just want you to be ready for what's coming later on. We're going to do kinematics of particles in rotating coordinate systems, and it's going to get a lot more complicated. But for now, all our kinematics of particles are just assuming that, that the coordinate system is holding the same orientation. Okay. Okay, so the first section is this derivative relationship. The second section is a chain rule approach. And we'll use that when the velocity vector is known as a function of a position variable. The third one is relative motion. Anyone remember relative motion from Physics 1? Yeah. I think, you know, different instructors emphasize it to different degrees, but it's going to be important to us. But it's just saying if you have 2 coordinate systems that have the same orientation, and you measure kinematics in one of those coordinate systems, figuring out what it would have registered if you measured it in the other coordinate system. Why you would care about that is not clear to you yet, but it's going to be important in this class. And then the last one is circular and spherical motion. And these two together, relative motion and circular and spherical motion, are going to be important together when we talk about linkages. And linkages are like, think of like robotics. You have multiple bodies connected by joints that are moving because you're applying forces to this one or this one and calculating the accelerations and the contact forces between the bodies as these motions happen. Okay, so we're going to spend a bit of time on linkages. It's useful for robotics and it's useful for biomechanics. And then any kind of machine it's useful for, but. Okay, so the first thing we're going to talk about is this relationship. The acceleration is the time derivative of the velocity, and it's the second time derivative of the position. These relationships are always right, you know, they always hold. Just be careful. Don't make the mistake of confusing these relationships with the acceleration is equal to v prime is equal to p double prime. Okay, this is not true. This is like a Schlummy relationship, you know, this is like, I don't know what variable you have, like take the derivative, maybe you get the velocity, you know what I mean? Like, you don't know what the variables are, you're just taking derivatives because you can. That's nothing, okay? This is what we want, like it's made in Germany by precision engineering. Like, this is the time derivative of the velocity and the second time derivative of the position. This is the relationship, this is garbage, okay? Okay, well, with these relationships, there's 2 directions you can go. If you're given the position, you can go to velocity and or to acceleration, you know. This you can think of as the easier one. It requires less. You're just taking time derivatives. And what makes this easier is that you don't have to worry about boundary conditions at all when you're going in this direction. So like, for example, let's say that you know that the position and we know it as a function of time is equal to t squared. And we want to know what's the velocity as a function of time and the acceleration as a function of time. Okay, I'm not given any boundary conditions because you don't need them. You don't have constants of derivation of, you know, differentiation. You only get those constants of integration when you're going the other direction. So in this case, you know, v is just equal to 1, 2t. That's, just to make it explicit, that's a function of time. And then take another derivative with respect to time, and you get that acceleration is 0, 2. So that direction is easier because you don't have to mess with constants. But the other way you can go is acceleration to velocity to position. You need to be given one boundary condition per dimension per step. And then you have to use those boundary conditions to find the constants of integration. When I say one boundary condition per dimension, I'm talking about like, well, if this is a one-dimensional motion and you only have position is just a scalar, velocity is just a scalar, acceleration is just a scalar, you only need one boundary condition. If it's a 2D motion, then position is an x and a y component, velocity is an x and a y component. So then each step you need two of those. You with me on that? Okay, so in this case, we did an example like this last time, but so let's say that we know that velocity as a function of time is equal to t squared cosine t. And we want to know what's the position vector as a function of time, given that at time equals 0, the position is 0, 50. Okay, so this rule says, well, we're taking one step in this path. We're going from velocity to position. So we need one boundary condition per dimension. This is a 2D problem, so we need two boundary conditions, one for x and one for y, and we're given them here. When t is equal to 0, the x component of position is 0, and the y component of position is 50. Okay? So I'm going to do the x1 first. The x component. So I'll write it as dx dt is equal to t squared. Separate variables. Dx is equal to t squared dt. Integrate both sides. X is equal to t cubed over 3 plus, I'll call it C1. Now we'll use the boundary condition. The boundary condition says if you set t equal to 0, you have to set x equal to 0. So 0 is equal to 0 cubed over 3 plus C1. So C1 is equal to 0. And so now I can just update this. I knew this function, I just didn't know C1 yet. Now I know it, so my final value is that x as a function of time is t cubed over 3. And now the y component, we have cosine of time, so dy dt is equal to cosine of time. Separate variables, dy is equal to cosine of t dt. Integrate both sides. Y is equal to sine of t plus C2. Now use the boundary condition. It says that if you set time equal to 0, you have to set y equal to 50. So 50 is equal to sine of 0 plus C2. So C2 is equal to 50. And so y as a function of time is equal to sine of t plus 50. And now you can put those two together into a single vector. And it says that the position vector as a function of time is equal to t cubed over 3 sine of t plus 50. Any questions about that? The example I did last time where we calculated, we started with a constant acceleration, you know, the acceleration of gravity in free fall, and integrated twice to get the position function and used the boundary conditions. I gave a boundary condition because it's the way you're used to seeing these constant acceleration equations. I used a boundary condition for the velocity and a boundary condition for the position. But if you're taking two steps like that, you actually could do it with two boundary conditions for position. You just have to solve it as a system of equations. Let me do one like that real quick. Okay, so let's say that we know that the acceleration as a function of time is equal to t 5t. So this is not a constant acceleration. It's, it varies in time. And let's say we're given, so let's say we want to calculate the position vector as a function of time, given two things. The position when time is equal to 0 is -4, 0. And the position when time is equal to 1 is 0, 10. Obviously I just made up those boundary conditions. But so those are the ones we have to use. What I did in the last class when I did a problem like this, I used a boundary condition for position, and then I used a boundary condition for velocity. It's a little easier to do it that way because you can do it in steps, but you can do it like this too. Okay, so how are we going to do this? Well, the first step is we can calculate let me start with the x component. So I'll write it as d x component of velocity dt. That's the acceleration. And that's equal to t. So dvx is equal to t dt, and we can integrate both sides. And so the x component of the velocity is equal to t squared over 2 plus c1. You with me on that first step? Okay, and now we'll do the second step. Vx is dx dt, and we know that's equal to t squared over 2 plus c1. Okay, let me stop here before I go on to the next thing. Like in past examples, once I get here, I always use the boundary condition to solve for t1. But notice we don't have any boundary conditions that'll let us solve for this, because neither of these say at a given time we know the velocity of x is this thing. So there's nothing we can do. So we just have to kick the can down the road and do all the boundary conditions once we get to an expression for position. Are you with me on that? Okay, so we have this. So now we go dx is equal to t squared over 2 plus c1 dt. We can integrate both sides, and we get x is equal to t cubed over 6 plus c1t plus c2. Okay. Now we have to use the boundary conditions. The first one says when time is equal to 0, x is equal to -4. So -4 is equal to 0 cubed over 6 plus 0 times c1 plus c2. Okay. And so this one tells us here that c2 is equal to -4. So now I guess I'll update, and I get that x is equal to t cubed over 6 plus c1t minus 4. And now I'll use the second boundary condition that says when time is equal to 1, x is equal to 0. So now I'll go 0 is equal to 1 cubed over 6 plus c1 minus 4. So we got 3 and 5/6, 3.83 repeating is equal to C1. And so update again, and you get that x as a function of time is equal to t cubed over 6 plus 3.83 repeating t minus 4. And now the y component, I guess I'm not going to do that because hopefully that sort of got the idea across. I guess because I made these boundary conditions up on the spot, I made it so that you could solve these as a, it was because I used this boundary condition where time is equal to 0. But if I had chosen 2 where time was not equal to 0, you'd actually have, what you'd come up with is 2 equations for 2 variables that you'd have to just solve as a system by substitution or reduced row echelon form or whatever. Okay. But that's the idea. If you're given, that's 2 boundary conditions for the position instead of 1 for the velocity and 1 for the position. Any questions about any of that yet? Okay, so this was all just this relationship that's always true. I should say this relationship, these relationships always hold. Well, they always hold no matter what. It has this sort of simple form when you have a non-rotating coordinate system. This is all non-rotating coordinate system. So now the next thing we're going to talk about is the chain rule. And we're going to use the chain rule when you know the velocity vector as a function of a position variable. So like, for example, what if you know that the velocity is a function of x? Let's say we know that it's equal to x 10x. And we want to calculate the acceleration as a function of x. Okay. Thinking of the relationship between velocity and acceleration in that schlubby way that I despise so much would make you think maybe you could just be like, I don't know, yeah, x is just take the derivative and you're done. But that's not how it works. You have to take the derivative with respect to time of this to get the acceleration. Okay? So what are we going to do? So, just a second. Let's call S our position variable. Well, the acceleration is the time derivative of the velocity. And if we think of that in terms of the chain rule, that says derivative of the velocity with respect to that position variable times ds dt, and this is a velocity variable that you've already been given. Or instead of variable, let me call that a velocity component. You already know. Okay, so let me do the example I wrote up here. So if you know the velocity is a function of x, is x 10x, then the acceleration as a function of x is dv dx times dx dt. Dx dt is the x component of the velocity, which is this. Do you see that? Dx dt, the definition of the x component of the velocity is dx dt. So now this is just going to be equal to dv dx is 110. We're going to multiply it by dx dt, which this relationship says is x. And so we get a value of x 10x. Which is not what we would have gotten. Hey, the acceleration is the same as the velocity. This is not what we would have gotten if we would have just taken the derivative of the velocity to get the acceleration. The reason we didn't get that is because it's a derivative with respect to time. Acceleration is a derivative of velocity with respect to time. Okay. Who's with me? Who likes this? Everybody? Okay, good. Yes?
How would that change if there were an x and a y in the velocity equation?
Yeah, we could think about that. I won't give you any problems like that, but then you would have to do partial derivatives, which is kind of beyond the scope of what we're talking about here. But so let's say you had, let's say that you knew that this was equal to xy, y, and then y cosine of x or something. And you wanted the acceleration. Then the acceleration would be the partial of v with respect to x times dx dt plus the partial of v with respect to y times dy dt. And yeah, you can totally do that. dv dx would be, so you'd have y here. Here you would have negative y sine of x. Dx dt is xy. And then you'd add that to dv dy. This would be x cosine x. You'd multiply that by y cosine of x. Multiply that out and add them, and that's your acceleration. But we're not going to do that because we're not doing any partial derivatives or anything. So this is secret. This is why we have the window blinds drawn. Okay. Any other questions?
So
Yes.
Why didn't the negative carry?
The negative, did I miss a negative?
Negative y sine of x. Wouldn't sine of x just be cosine of x? Negative y sine of x would be
Here?
Yeah.
Well, you could multiply it through and you would get xy squared for the top and negative xy squared sine x for the bottom. You could simplify it a little. Yes?
So then for adding the third dimension, it's just adding the partial with respect to z and then dz.
That's right. Yep. But you won't have to do any of that. You'll only have to do stuff like this, where it's either a function of x, or it's a function of y, or it's a function of z. Okay. Okay. I'm going to add a little complexity to this next time, but this is the heart of this idea of using the chain rule. Okay, that's all. Have a good weekend. Except for those of you who I'm going to see in 7 minutes.
And George,